Hello everyone, welcome to the class ECE317, the digital signal processing. Today we will start a new chapter 6, about the structure of systems. Actually we just finished chapter 4 and we jump chapter 5, go to chapter 6. After chapter 6 we will go back to chapter 5, then followed by chapter 7, because both chapter 5, chapter 7, they are regarding with the systems, filters, design something, right? Okay, so now we go to chapter 6. All right, it's a ECE317. This will be the 11th week, Monday's class. Okay, and structure chapter 6, structure of systems. Structure is just kind of I can just graph for the examples. For example, you have H1 of S, you have H2 of S, then you put them together, connect them together by this way. Now this is the structure of a system. Maybe we have something more complex, like here we go back, we have H3 of S, and do a summation here, like this. It's different, right? And maybe more like you are also consider like here you have another H4. Here's a summation. This is also different, right? So structure is you have some parts, some pieces, you put them together, then you have a whole system, right? And how to build the whole system by these pieces, that is the structure. And for each H1, H2, H3, 4, we can call them as subspaces, right? HIs, S, they are subsystems. And the smallest subsystem, you can also call them consider them as basic pieces to build a system. We have these. We say the basic pieces to build a system. We have 3. One is just a summation. If you have several signals, you do a summation. You have x1 of n, x2 of n, x3 of n, maybe more, maybe less, but at least 2, right? Add 2 together or more together. Then this side will be the output of the summation. There will be x1 plus x2 plus x3. Okay, it's a summation. It's the first basic piece. And the second one, it is just times a constant. So usually you just put constant here, like a. Then this side is x of n. This side will be a times x of n. And if you want, you can put a triangular here or an arrow here. This is a constant gain. And the third kind of basic pieces similar with these, but now it is a function. Which function? It is the 1 over z, x of n. Then this side will be what? This side will be x of n minus 1. This is a delay. Unit delay by 1. In Z domain, this is x of z times z to negative 1 equal to the z transform of x of n minus 1. Right? This is a basic feature of the z transform. Right? So we can build a system by these three basic pieces. Of course, you can have a structure with less details. Then you can just write in this one, and HI might be something other than this, complex than this. Right? But if you want all the details of a structure, then you need each part is something like this. Then we can have, I can put the example here. Different page. Example. We can consider summation. Similar with that H1, H3. So, but I put like here. I put 1 over S here, 1 over Z here, 1 over Z here, or Z to negative 1 here. I have a delay, and here I put a 2. It's coming up, and I separate. Here's another delay, and here's a summation, and separate. Okay, here's no delay. Here's just a number like a negative 4. All right, then I have a structure. Right? I can have a structure. Well, you can have a lot. You can just put these kind of pieces together. Then you can have different kind of systems. And we have another style. Actually, these are the block diagrams. Block diagram. You can say this is block. Right? Basic piece. This one is a block. We can also use another way to give the structure. It's a signal flow graph. Signal flow graph. Signal flow graph. Then we still have three basic pieces, but we write in this way. This is summation. 2m. This is summation. All right. You don't need to put add here. You just put a small circle, but you have several paths go into it. So this is summation. And the second one is a gain, constant gain. Then you just put a like here. And then for the delay, you put the z to negative 1 here. All right. This is a constant gain. This is the delay. And here the thing is like this. Each small circle, it is a signal. And this one, with some, I put some g here, a function. Function g. G might be a, might be z, 1 over z. If you want if you don't want all the details, maybe here's some other functions. G could be maybe some other function, right? So each small circle is a signal, and in this structure, along each path, it is a signal. So you do not have a circle for signals. Signal just something go along the path. Right? Here's the signal will be those small dots. Yeah. Then, for example, I use the same thing, same example. Now I give the let's say this is a 1. I'll give the signal flow graph of 1 of example 1. That is like this. Here's a summation, right? Here's a summation. So this one go to here, and here's another summation, like this. This. Here's a -4. Here's a z to -1, and here's a go ahead and to the output, and here we need a going down with a 2, and here's going up with summation. Here's z to -1. Yeah, so like this. Okay. So this is a same with that. Yeah, looks also similar. Just here you need a cross. You need a rectangle to go to cross to cover these 1 over z. Here you just put 1 over z here, z to -1 here. You don't need to put a block around it. Okay, so this is the structure. And then we have the problem how to find like a transfer function from structure. Find the transfer function from a structure. You need to go over the graph and list some equations and make some simplify, right? I still use that one. Example 1 continuously. Okay, I give the graph again. This one, I have a summation. Here's 1 over z, a delay. Then going out, this is output, and here I have a feedback times 2. Then go to here, z to -1 delay, and this one, this pass, no delay, just -4. And here's a summation, and here's another summation, right? This is the graph, and this side is the input, this side is output. Okay, I want to find the relation between input and output. Then you need to go over the structure, give some equation. So firstly, you need to check how many basic pieces do you have. Here's a summation, right? This is one. Here's another summation, and I have delay. Here's another delay. Here's a constant gain. Here's another constant gain. Okay, so we have 1, 2, 3, 4, 5, 6 kind of pieces to put it together. I have the whole structure, right? Then you go over all the pieces. Each piece you can have an equation. All right, we check the first one. First one is a summation. Summation of these two, you get the third one, right? So you need some notation to denote them, right? Like I use W1 for this, W1 of n, and this is W2 of n. Then I have W1 of n equal to x of n plus W2 of n. Okay, this one, I have the equation. Then the second one here, we can see this side is W1, go over this delay, then the output here is just y. Okay, so y is x1 of n with a delay. So I have y of n equal to W1 of n with a delay. Right. If you want, you can also use z domain to represent it. This will be y of z equal to z to -1 times W1 of z. You can also use this kind of equations. You can use either way. For each dot, you give an equation. You can work in time domain or z domain. But remember, just in one domain. If you here I use time domain, then I use all the equations just in time domain. If I use z domain, then all the equations should be in z domain. All right. Okay. Now I just use the time domain. All right. I have this one. I have this one. Okay. Then I check any. I pick any one like this one. This is also summation. So these two signals do summation. I have W2. So W2 of n will be summation of these two. So here you need to give some variables to denote these signals. But you can also just if you can save something, you can look at it. This one is coming from here. It's coming from this y, right? Y times 2, then delay, you get this one. So this place is 2y with a delay, right? Here's a 2y with a delay. So I can just put 2y of n minus 1, right? And this path is also y times 2 times negative 4. So actually totally negative 8 times y, but without the delay. Okay, then I can have 3 equations look like this. If you want, you can also write, you can introduce more variables like 1, 2. I can use W3 here and W4 here and W5 here. And okay, you can write in this way. Here, if you want, here's a W6 of n. You can give every path, you give the signal inside this path. Then if you give these things, then W2 will be summation of W3, and this is 4, right? And W4 and W4 of n, right? This is W2, is this 2 summation, and the W2 is delay of W5, and the W3, it is negative 4 times W6, and the W5 actually is the same as W6, right? These two are same signal, and both are 2 times y of n, right? You can also give more equations, but here you just plug in what is the W2 here. You have W5. W5 is 2yn, so you have this 2yn with a delay, right? This is delay, and minus 8 of minus 4 of it, and 8 of it, 8 of yn, right? So you can write in this way. You have less equation. If you one equation, you can also write this 4. But after you get equation, you need to try to erase those w, and you can still have these. Okay, now we keep working. We need to cancel those W1, W2 from these equations. We only want the equation contain x and y. So we can replace something just by x and y. Okay, the second one, right? 1, 2, 3, right? So 2 give us W1 and minus 1 equal to y, right? So we can replace W1 by y. Then the 1 I have W1 becomes 1 I have W1. Now W1 is just y, but the index here in this equation, the index of y is 1 more than index of W1. So here's W1 of n. If I rewrite this as y, it will be y of n plus 1, right? Okay, equal to x of n plus W2, right? No, the first equation. And second equation we use just this one. And the last equation, third equation, do we have W1? Oh, no W1. Okay, we're done. So we change W1 by W2 here. And the third equation, actually we have W2, right? W2. Third equation, W2 equal to something, right? So we can replace W2 by 3. All the equation, just this one, right? This is just only one we need to consider now. Replace W2 by this one. Okay, so I have y of n plus 1 equal to x of n plus W2. W2 is, okay, totally same, right? Both with index, time index n, so totally same. Then it is 2 of y of n minus 1 minus AY of N. Alright, almost done. We need to put in a standard way. We put all the input in one side and output in another side. So here's y of n plus 1 minus, I use this plus, okay, plus y, 8 of y of n, and minus 2 of y of n minus 1 equal to x of n. Right, we have the equation. One side is all the x terms, the other side is all the y terms. However, we have y of n plus 1. Usually we want the highest index on y will be n. So I write this as y of n. Then this will be y of n, now will be y of n minus 1, right? And the last one is minus 2 of 2 times y of, this should be n minus 2. I will move every n by 1 less, right? So make this is n, this will be n minus 1, this will be n minus 2. And x also n minus 1. X of n is n minus 1. So we have the equation looks like this. Yeah, we have equation looks like this. Alright. Okay, so this is the example how to find the equation. It's a fly. How can find the equation from the structure? Yeah, you can just work like this, right? We know each block, each small piece, basic pieces, and go over every pieces. You give the equation, and then try to reduce some actual signal. Then you have equation just related with input and output. Okay. And for some special case, we can write the structure directly. So for some structure, we can have the transfer function like this. Why is it like this? If you have h1 of s and h2 of s, you have small two pieces, and they are connected together. So this is x, this is y. Then the overall structure, it is h1 of s plus h2 of s. Actually, we have this before, right? This is a parallel connection of two subsystems, and the whole system will have transfer function just to summation of these two. And another kind of thing is h1 of s followed by h2 of s. This side is x input, this side is output y. If we have a structure like this, then the whole thing is h1 of s plus times h2 of s. Okay. We also have this before, right? This is a parallel connection, cascade connection. Cascade is a parallel connections. And the third one is like this. h1 of s and h2 of s, but the connection is like this way, go back like this. It looks somehow similar like this, but this path is go backward, right? To go back. Then this one whole thing is h1 of s over 1 minus h2 of s. This is a feedback connection. Feedback. Right? This is a feedback structure. If you have several pieces, you can think the whole structure looks like this. Then we can go back to the example again. example 1 continuously. Okay, I use signal flow to give the graph. Okay, this is z to -1, z to -1, and z to -1, z to -1, and here I have 2 and -4. Here's a 2, here's a -4. Alright, so for this one. Now we can also just consider it is a kind of a connection. We have several pieces, connect them together. I have whole thing, right? You can see these two paths. So this part, this is a parallel connection, right? Right, this part, just this part. This is a parallel connection of z inverse and -4. So this whole part is z to -1 plus -4. Alright. Then that one, I say this is 1. Now one equivalent ways I write in this way. That means they are not same, but they have same function, right? They have same function. It will be here's z to -1, and here it go around this way. Here's a 2, and this part now is a z inverse -4. Okay, so we have a structure look like this. Alright, then the whole thing is what? From 2 to here, these two actually both are the feedback. This is feedback, and this part is a cascade connection. This is a cascade connection. So this is a I write one again. This is z to -1, and here is a 2 of z -1 -4, right? Because this two is this is a cascade connection. So you need times these two together. All right. Then we say finally we have this one by that from the feedback formula. Your z inverse over 1 minus this part is 2 of z to -1 -4. And let me simplify. I will have -2 of -1 and +1 minus +1 plus 8, so +9 z to -1. Am I good? 8 is it 9? Why get 8 here? What is my previous answer? It should be same thing, right? Oh, I get something wrong. This one is delay, no problem. But here I have 1 and the delay 8 delay 2 delay. But here I get something wrong, I think. This is -4. This is z to -1, z to -1, and 2 -4. So these two will be z to -1 plus -4. Yeah, no problem. And times 2, so it's 2 times z to -4. And then z to -1 over 1 minus, oh, I forgot this. Yeah, I put, sorry, it's here. I lost this one, h1 of s, the formula. Okay, the formula should be this. That's my fault. Yeah, the formula should, so these 2 times together is put it here. Then this place, it won't be this. It will be, yeah, this is not good. It will be, so the one will have equivalent ways. Now is z to -1 in the numerator, and denominator it will be 1 minus the denominator, this part, the feedback part, times that z to -1. Okay, This one should be good. And numerator is same thing, and denominator it is 1 minus 2 of z2 negative 2 and plus 8 times z2 negative 1. If I write in the order with z, it will be 1 plus 8 of z2 negative 1 minus 2 of z2 negative 2. Okay, we have transfer function look like this. And the previous one, we work in the time domain. We have this one. This is the equation in time domain. Compare these two, are they same? Yeah, same, right? We can have the z for the transfer function. This is 1 plus 8 with 1 delay, and minus 2 with 2 delay, and z for x I have 1 delay. Yeah, so we have this, and then we have this one. This is transfer function. This is a difference equation. Yeah. Okay. All right. Now let's consider consider another direction. So we have two directions, right? So from structure to equation to transfer function or difference equation, right? So okay, we know how to do it. Nothing special, just go over the structure and try to give a transfer function or difference equation. Now we want to go back. So transfer function to structure. Yeah, we want this one. Problem 1. Okay, we know how to do it, right? Now problem 2. Suppose you have transfer function. How to give a structure? Here we need two basic things. So first one, we consider the case. Consider FIR field. FIR field. What is FIR? That means finite impulse response. Finite impulse response. So FIR, finite impulse response. That means h of n will equal to some h of we start from h of 0, then h of 1 until h of some n. That's it. When n larger than this capital N, h of n is 0. So that means we only have finite h, they are non-zero value. Maybe here I have n plus 1, right? Maybe more, maybe less, because some of these h from h0 to h capital N may be 0. For example, if h1 is 0, h0 is not 0, then this is 0. All these are 0, but last one, h of n, is not 0. Right? That is the case. So you will have finite non-zero values in the FIR. Right? Like in this way, at most you have n plus 1 non-zero values of h. When n is larger than this capital N, they are zeros. And for n smaller than n, smaller than 0, I'm sorry, not n. For n smaller than 0, in this side, here first one I use h of 0, right? Maybe you have h of negative 1, h of negative 2. For those one, we always think h of n equal to 0. That means causal case. Yeah, we build the system. We just build the causal system. We have a causal system. If the system is not causal, yeah, it's hard to give a structure. The structure itself is something You can run it. The feeling is like a real world, right? Okay, for this kind of things, FIR. So what can we say for these FIR field? You can also call it the FIR system, but people like use filter to call the system in this case. What is h of z? By definition, it's a summation of h of n times z to negative n and run from negative to positive infinity. But now we know h of n are zeros. Only when n run from 0 to capital N, it is not 0. So h of z will looks like a kind of polynomials on h to some negative n. Right? This is h of z. Then we can write this in equation. What will be the equation? You see, this is a fraction. Numerator, this is just numerator. Denominator is what? It is 1. Right? So in equation, the IO equation, right? Output equation. We will have y of n, right? Just y of n. Here's 1. So this is just y of n. We're equal to all of these. It's a summation n equal to 0 to capital N, then h of n times x of n minus, okay, there's a k here, and minus k, right? It's n delayed by k. You hear I use a k. It's a k. So hk times x delayed by k, and k run from 0 to n. And what is this one? Actually, this is just h of n convolution with x of n, right? So you can have these directly from the convolution. You will have same thing. And we can write more details. When h is 0, when k is 0, I have h of 0 times x of n minus 0. Right, n minus 0, just n. Then h of 1 times x of n minus 1. And so on, until h of n times x of n minus capital N. So we have equation looks like this. Then the structure will be same thing with this one. We can use, okay, I just use the signal flow graph, alright. This is x, this is y. Then this place I just times h of 0 here. Along this path is times h of 0. So this is the first term. And second term times h1. So I can work like this. H of 1 is here. Right. So x, I need a delay here. I need a delay in which side? Doesn't matter. You can put the both sides like I put it here. Z to negative 1 here. Then you see this xn go here, xn, then times h1, then delay by 1. So it's this one, right? X delay by 1 times h1. Then do a summation, you have this one. And okay, I can put second one. I still put delay here. This is h of 2. This will be the term after this. Here should be h1, h2, h of 2 times x of n minus 2. So this is x, right, times h2 and the delay by 2, right? X times h2 and delay by 2, right? So this is next term. Then we work in the same way until the last one. This is a, here's a delay, and this is a h of n. Okay, so the structure just looks like this. Yeah, just look like this. It's going down, and at each level you have a branch. The signal go in that way, and this is some edge. some value of h, and then going up along this path, each part you need a delay. You need delay. The first one no delay, just go ahead. Second one you have one delay. Third one you have two delays. Right? Yeah. So this gives the structure of that. And we can also put the delay in another side, right? Put delay in that side, it also works. So or I put it this way. Sorry, or wrong direction. This way, come up. It's coming down, it's up. It's coming down, it's going up. And here's edge of 0, edge of 1, edge of 2, until edge of n. And the delay is here. Delay here, delay here, delay here. But yeah, you can put delay in both sides. But just one side. You cannot put both sides with delays. If here both sides you have delay, you are delay times h1 and delay again. That's different. Alright. Yeah. So just you put delay, all the delays left, all the delays right, or all the delays left. So both are same thing. Okay, so this is the structure of FIR field. FIR field. Okay. Then the second one, we consider the other side. Actually, it's a IIR field. One consider okay, but we consider the simple case. We consider an all poles field. All poles field. In this case, h of z will equal to 1 over something. Let's say some z, some 1 minus a1 z to negative 1 minus a2 z to negative 2 minus a n z to negative n, like this case. Yeah, I put minus. The most simple case is just one term. That means 1 minus a1 z to negative 1. Right? That is a common used term in z transform. Right? So I put negative. If you want to put plus, then this one go back to time domain. You need a negative a1 to the n power. Right? Now I use minus a1, so just a1 to the n power. Yeah, for convenience, I write in this way. And when you get structure, you will see this one will be reasonable. Okay, for this case, then how to give the structure? Actually, what is structure? Structure gave you a way to calculate, right? Like this yn. What is y of n? It is xn times h0 plus hn times h1, xn times h1 with a delay. Then xn times h2 with 2 delays, right? You add them together. So the structure, it is also kind of how to calculate. So you can consider these two ways to view it. You can think this is kind of a circuit. You can think just similar, right? It looks like a circuit. You can also think this is a process of calculate. Some place you need to do a summation, like here, right? There are summations. Some place you need a times constant, and some place you need to make a delay. You need to save it in some variable and use it later, right? So this is give you a schema of calculate, right? Give you a plan to calculate, how to calculate. Then here you want to give a structure. If you just look at this, it's hard to think about it. But you write in equation way. That will give you a way to calculate the output from input, and that one, it will give you a structure. Okay, we look at the equation way. Then we have the input output equation. It is y of n, right? The first one. Then minus a1y with 1 delay minus a2 y with 2 delay minus until minus a n with capital N delay y, capital N delay, and equal to, okay, this side just x of n. Okay, because this is 1, nothing changed, just the input. Then we can have, we want what is y. Y at time n will be x of n plus a1 of y of n minus 1 plus a2 times y of n minus 2 plus until plus an times y of n minus n. We have this. Okay, then we can have the structure. You can think like, what is y of n? You put y of n this side and x of n here. It will be x, y of n go to, right, this is xn, and I need one more thing is a 1 times delay of y. Okay, y is here, so suppose like this way is y, right? This is y. I go back, I just go back like here. I go back with a delay, right? With a delay, and times a1. I do a summation here. You got it? So you see, this is what? This is a y is xn plus a1 with 1 delay of y. Okay, these two are same. Here I just connected. Here's nothing. That means it's 1. So this signal is as same with this signal. These two are same values, right? And this signal is Z1, and that one is summation of these and these, right? Okay, but we have more terms. Then I can put it here. This one A2, so I need a delay here with constant gain is A2, okay, and so on. The last one is here I need one more delay, and here's a constant an that's coming up. This side is coming down, right, like this. Alright, so this is a quite similar with this one. You see, this one is a structure of FIR field. Okay. Just look like this. All the paths is going forward, right? All these are going forward. This is a FIR field, and this one, it looks similar, but all these paths is going back. We call them feedback. We have a lot of feedback. All of them are feedback, and these give us all poles field. All poles field. It's just y is xn plus all of these terms. All of these terms. These are a1, a2 to an. Yeah, a1, a2 to an, right? But here's minus, here's a plus. And go back here. This one, these are the h0 to hn, h0 to hn, right? h0 to hn. All right. Yeah. So you put all the coefficient here. Yeah. Here you do not need to put a minus. So hn here is just hn. All right. Okay, that's all for today. See you next time.